and the whole group for the kind invitation to come here. It's always a pleasure to be here. I mean, to meet old friends, to make new friends. So thank you very much for the invitation. Our goal today, this is a joint work with my colleague Herman, and our goal today is to propose a connection, and we hope an interesting connection, between an old idea of schematic inference rules in natural deduction and a more recent work in the area of second-order propositional logic, which is called atomic polymorphism. The structure of the talk is very, very simple. I hope it's going to be very short. I'm going to revisit briefly schematic rules, the basic ideas of schematic rules, and then I'll propose an application, very quickly application of these schematic rules, which is a very general translation of a certain number of logics into minimal implicational logic. And then I will revisit what is called the Russell-Profits translation, which is present in Profits' monograph in the chapter in second-order logic. And then I will present the system FAT that has been proposed in 2013 and 2014 by Fernando Ferreira originally, and then Fernando and Gilda Ferreira. And then the new thing, I will propose an application of the system FAT, and this application is really the connection between FAT and these schematic rules. And then I'll just mention some future work that I think can be done in this area. It is, in a certain sense, it's really a work in very, very traditional old-style proof theory, in a certain sense. You'll see that we're going back to the 60s, 70s, and then move to the natural, right? I think that everybody that works with natural deduction has posed these questions to yourself, and there are several different answers to these questions. I mean, where does the naturality of natural deduction lies? You can have an answer from category theory, you can have an answer from algebra, you can have an answer from philosophy, from psychology, I mean, from many, many fields to explain in what sense natural deduction is natural. There are two traditional answers to these questions, and I'm going to rely in Doug Profits' monograph. The first answer is natural deduction is a faithful representation, right? And the second answer is connected with meaning theory. This is a quotation from Doug Profits. In the first place, natural deduction is natural because there is a similarity between natural deduction and intuitive informal reasoning. The inference rules of the systems of natural deduction correspond closely to the procedures common in intuitive reasoning, and when informal proofs such as are encountered in mathematics, for example, are formalized within these systems, the main structure of the informal proofs can often be preserved. So this is the idea of faithful representation, right? The second point, the second reason, which is connected to meaning theory, is that Dog says Genson's variant of natural deduction is natural also in a deeper sense. His inference rules shows a noteworthy systematization, which among other things is closely related to the interpretation of the logical science, right? And with respect to the inference rules, with one exception, right, the inference rules can be divided, can be categorized in two kinds, introduction rules and elimination rules. And this brings two new questions. Right? What's an introduction rule for an operator, and what is an elimination rule for an operator, right? How can we characterize in general terms, conceptually, what is an introduction rule and what is an elimination rule? This is Profits' answer, right, that you can also find in his monograph. The introduction rule for a logical constant allows an inference to a formula that has the constant, and the elimination rule for a constant, on the other hand, allows an inference from a formula that has the constant as principal side. But I think that Dog, after some years, realized that these answers, answering what is an introduction rule and what is an elimination rule, does not answer to the more general question, what is the most general form of an introduction rule? What is the most general form of an elimination rule? What are the components of an introduction rule and what are the components of an elimination rule? And in 1978, Profits proposed an answer to these more refined or elaborated questions. What is an introduction rule and what is an elimination rule? And this answer was carried out by means of his schematic introduction and elimination rules. So what is in very simple terms, what is a schematic introduction and what is a schematic elimination rule. And a schematic introduction rule for an operator phi, an arbitrary operator phi, should give us, everything that we need, in a certain sense, in order to define the introduction or a set of introduction rules for these operators. For example, we would like to have a conclusion, we would like to have some premises, and we would like to know if the introduction rules allows us to discharge some assumptions on the top of some premises. And in fact, this was exactly, the general framework of Provitt's schematic introduction rules in 1978. So, just mentioning some related work, from Kucherev from 1968 and Zucker and Trageser from 78, and a little bit later, Schroeder-Heister, 1984. Several works from Schroeder-Heister. I've just mentioned 3 of them. But this is a very, very old picture. See, it was not even, typed with a computer. It was typed with a type machine, right, of a general form of an introduction rule. So you see there that you have the conclusion, phi for the operator phi, and you have the premises, a certain number of premises, and then you have some information concerning the assumptions that can be. The main idea at that time is that given the rule, one could extract, so to say, systematically or almost automatically the corresponding elimination rule, right? So the most important thing, as in Genson's spirit, was the introduction rule. The introduction rule would fix the meaning of the operators, the logical constants, and then the elimination rules would be a kind of consequence of this meaning that is fixed by the introduction rules. And a possible elimination rule, general elimination rule for an operator phi would have this form, right? That we have certain derivations of some minor premises, i.e. the assumptions that we discharged in the general introduction rule we now have as further minor premises that we have here, and here we have the major premise of elimination rule. I think that people that are used with natural deduction clearly recognize that the model for the elimination rule is the disjunction elimination, right? So in the spirit of von Plato and Saranegri and from Schroeder-Heister, it is a kind of a generalized elimination rule where but the spirit or the original model is disjunction elimination, right? This was the original Dogg's elimination rule. I will not go into that. And Dogg, in 78, also proposed, that is something that von Kucherev has done in 68, also proposed a kind of constructive version of the well-known classical truth functional completeness theorem. That we know that a certain set of classical operators or propositional operators is complete if they can be they can define all functions, right? So Dogg proposed in this 78 paper a kind of operational version of the truth functional completeness. And the theorem would be that if the introduction and elimination rules for an operator 5 are instances of the schematic introduction and elimination rules, then phi could be intuitionistically defined by the usual intuitionistic proposition operator. So this is the definability theorem, a very, very nice theorem. But the schematic rule, the schematic elimination rule that Dogg used was not strong enough to obtain this theorem. So this was the problem that was left by Dogg's 78 paper was solved by Peter Schroeder-Heister with his notion of higher level rules. It is a very, in fact, this is the title of Peter's paper, A Natural Extension of Natural Deduction, which is a very nice and interesting natural real extension. In natural deduction, we are used to assume a proposition and derive something and discharge proposition, discharge formulas. And then in Peter's system, he also allows the discharging of rules. So I can assume a rule and then I can derive something from this rule hypothesis, and then I can have rules of high level that allows us to discharge rules. So I can have rules that discharge formulas, rules that discharge rules, rules that discharge rules that discharge formulas, and etc. And then I have a hierarchy of rules, and with this more powerful natural deduction, Peter was able to prove the Dogg's theorem. But in the 90s, right, a student of ours from PUC proved a weaker result. She was able to prove that we could define a translation function that even using not the higher level rules, would allow us to prove a kind of weak completeness theorem, right? I would not have a definition of the operator, but I would be able to prove that the translation function would preserve derivability, right? This is a nice result. It's not what the result that Dog wanted, because Dog wanted to internalize the definition, but this was a kind of external use of the definition in terms of derivability. But in any way, it's a nice result. I'll go very, very fast through this idea of defining a very general translation, right, based on these schematic rules. The main idea is that it may seem very general, but it's interesting that suppose that you have a system of operators with the schematic rules, introduction, elimination rules that satisfies the subformula principle. Then this operator, this system can be embedded into minimal implicational logic. This is the result, and this was obtained by my colleague Herman. So again, we have a new form of a general introduction rule, and the main idea is to rule into a kind of axiom. The new variable here will be a representative of the new operator that we are defining. This is inspired, so to say, in Statman's translation and some old translations from intuitionistic logic into minimal logic, in fact. Right? I'll go fast. I would not, otherwise I would not have time. This is the again, a new form of the general elimination rule, and again, we associate with the elimination rule in an axiom, and then we use these axioms, an introduction axiom and an elimination axiom, to define some translations, right? I do not have time to go through all these details, and the main result is that if take a propositional logic satisfying the subformal principle with respect to its schematic reduction elimination rules, and consider a translation star from formulas of L into minimum implication logic, and then we have preservation of provability, of demonstrability with this translation, right? Let's connect our schematic rules with atomic polymorphism, and to that we need to know a little bit what is atomic polymorphism. As I said in the chapter on second order logic in Pravitz's monograph, Natural Deduction, right? He defines this interpretation of this translation of the intuitionistic propositional operators of the bottom, of conjunction, and of disjunction into this second order fragment of second order propositional logic, right? With just universal quantifier and implication. So he could embed intuitionistic propositional logic, full intuitionistic logic within this fragment. But there, in that chapter, the fragment was, the full fragment. We could have instantiations of the universal quantifier which were not predicative in SSSS. We do not have the subformula principle. We lose a lot of our good induction measures in this second order system. A very interesting idea, a very nice idea, was proposed by Fernando Ferreira in 2013, if I'm not wrong, and developed by Fernando and Gilda in 2014, which is this system FAT, which is the name FAT, right, is to remind us of the system F, right, and the at is atomic. It is a kind of system F, relativized to atomic, to an atomic flavor in a certain sense. What is this atomic flavor? Main idea, the language, again, is the second order propositional language restricted to universal quantifier and implication, right? Which is a very restricted language. And the rules are the natural deduction rules. The elimination rule for the universal quantifier is restricted to atomic instantiation, right? So in the application of the universal quantifier elimination, can only instantiate with a propositional variable. So this is why it is called FAT of the universal quantification elimination to atomic instantiation. Restriction, these atomic instantiations, we get the subformal principle and good inductive measures. I will measure right away. A second important remark is that although instantiation to atomic instantiations, right, we have in this system this very nice and surprising property, which is called overflow in flat, which is that for these specific formulas, for the formula that interprets or translates the bottom, for the formula that translates conjunction, right, and for the formula that translates disjunction, it is possible to deduce A implies C, 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 A implies C, C. This is not. I'm not extending, right, the universal quantification elimination to allow any instantiation. I'm claiming that for these specific formulas, right, I can deduce. It's not an application of a rule. I have a deduction, right, from these assumptions to for an arbitrary C, right, and with the atomic restriction and with the overflow, this is just the proof that I can obtain from for every x, A implies X implies A implies X implies X, which is disjunction. It is the translation of disjunction. I can obtain D implies D1, D1 implies D2, D1 implies D2 as a kind of instantiation of X, right? I will not go through the derivation. I mean, it doesn't work right. And using this FAT system, right? Fernando and Gilda defined what can be. I mean, they did not call it like this, Provid's translation, but I could call it Provid's translation or Russell-Provid's translation, right? Which is this one, and only if this translation is proved in FAT, right? Which is a nice paper. In one of the directions, Fernando did not. I think he has a syntactical proof, a proof theoretical argument, but the one that I have seen is model theoretic, is using models in order to guarantee, I think, this direction here. So this is just an example of how to use the translation in order to translate not only formula, but to translate derivations, to translate the rules of the system, right? Suppose that I had disjunction introduction, which is a quite easy rule in a certain sense. This rule now is translated in our system in this rule here. I assume A implies X, and then by modus ponens I have X, and then I vacuously introduce B implies the arbitrary choice of this B here. I mean, this B comes from nowhere. It is the same that we have here. This B implies X comes from nowhere, right? Strong normalization for FAT. As I said, what is interesting, one of the interesting things about FAT is that it has good inductive measures. And one of the applications of these good inductive measures is that we can define reducibility predicates very easily in the same way that we do it for the usual first order logic with implication, conjunction, for example, in the universal quantifier, as Gerard does in proofs and types books. Here I did it for a kind of typed version of natural deduction because of the size, right? It was easy to define in terms of a typed lambda calculus here. So if T corresponds to just an atomic type, then it is reducible if and only if it is strongly normalizable. If T is of type implication, then T is reduction rules, as Pravitz does in his strong validity concept, which is his version of the reducibility predicates. And with the reducibility predicate, we can prove a strong normalization for the system FAT. FAT satisfies very, very easily in the, the proof is exactly the same proof that you can find in proofs and types as Gerard's proof inductive measures. So we have a nice, traditional, good reducibility predicate, and you can use the reducibility predicate to prove a strong normalization for FAT. And this was the main aim of Fernando and Gilda when they find the atomic polymorphism, the system FAT. His main idea was to use the system FAT as a kind of a meta-system to investigate the proof theory of intuitionistic propositional logic, right? For example, in the case of intuitionistic propositional logic, one traditional problem, for example, in a Provid's style of intuitionistic propositional logic, one traditional problem is disjunction elimination. Because we have permutative reductions, what to do with permutative reductions. Gerard would say, oh, this bureaucracy that is introduced by permutative reductions. But disjunction always presents some problems with respect to inductive measures, because the conclusion of disjunction elimination can be more complex than the major premise, for example. The conclusion C, the usual conclusion C of disjunction elimination may be more complex than the major premise A or B. So the aim with the system FAT was to use the system fat as a meta-system to investigate, to analyze the proof theory, I mean reduction sequences, for example, in the traditional intuitionistic system I for intuitionistic propositional logic. And this is what they did, right? They embed I into fat, and this result depends on the instantiation of the flow, and then they show that beta conversions in I, in the intuitionistic system, would correspond to beta-eta conversions in the system fat. And the idea is very nice, is that if you have a derivation pi in intuitionistic logic, right, then you look at its translation, pi fat, right? And now suppose that you reduce by means of a beta reduction pi to pi prime, then you will find, right, a reduction of pi to a certain pi prime fat, such that pi prime fat is the translation of pi prime. So the diagram commutes in a certain sense, right? And then it is easy to show that if you have an infinite reduction sequence here, you could imitate this infinite reduction sequence here. But given that you do not have infinite reductions, that you are investigating, right? So you could see that the universal quantifier is just doing the job to say that, because again, the universal quantification, in fact, is just doing the job in the translation to say that this is, so to say, arbitrary. This is the only point in the sense. Okay?
Already was.
Yes, yes, exactly. Okay. So I'm almost finishing. Let's now connect the schematic rules and the system fat. So the main idea is let phi be an operator given by the rules. For example, this rule here. I have a set of assumptions gamma 1, and then I have a premise pi 1, I have a set of assumptions gamma 2, and a premise pi 2, and then I introduce, by introduction, phi of pi 1, pi 2, right? And then I associated to this phi introduction rule, this general elimination rule, and now I'm using Peter's more general rules that I discharge, not only assumptions, but I'm discharging these rules here. The idea is that to use fat translation, and this formula will translate this operator. This operator, using this elimination rule here, is translated into this formula. If I have two introduction rules for an operator phi, right, and then I could use this more general elimination rule, extract this elimination rule from the introduction rule, or the two introduction rules, and then I could use this translation here as the translation, in fact, of the operator phi. And what is, to simplify, what is the idea? If you have an operator with just one introduction rule, right, then it will be translated as conjunction. If you have an operator with more than one introduction rule, then you use the scheme of disjunction to translate it into this general language. So if your operator can be defined by means of schematic introduction rules and schematic elimination rules, these operators can be defined and can be interpreted in the system fat, right? And if it can, yes?
You still have overflow?
Yes, you still have overflow. Yes, you still have overflow. And then we use fat to do the proof theory of phi, right? As it was done for intuitionistic propositional logic. So I could use the strong normalization theorem for this system phi. In fact, I do not have an example of a concrete phi to show a beta reduction for the phi, how to reproduce it. Your question is nice. It would be shown this way, how you would reproduce the beta reduction for phi in terms of fat. We have a flattening problem. This problem was called to my attention by Peter Schroeder-Heister, right? I don't know if I have time, yes, maybe. What is the flattening problem? Suppose that I have an operator star with these two introduction rules, right? I assume pi 1 and I derive pi 2, and then I have pi 1 that implies pi 2 and pi 3, and then I have a second rule that is pi 3 that derives star pi 1, pi 2, and pi 3, right? We don't know yet what is a star, right? And now suppose that I have a second operator, which is similar to this the operator star, but now I have pi1 deriving pi3, and then I derive star pi1, pi2, pi3, and then I assume pi2, and I derive pi1, pi2, pi3. So let's go back. Here I have pi1, pi2, and here pi3, and in double star I have pi1 to pi3, and pi2, two stars, pi1, pi2, and pi3. And what's the problem? If I have these two operators, and if I do not want to use Peter's higher level rules, the elimination rules for these two operators is the same. I cannot distinguish them from the elimination rules, right? So, and these two operators, they are not intuitionistically equivalent. Now, you're thinking, what are these operators? The first operator, star, is pi1 that implies pi2 or pi3, right? And it is easy to see that it is that. Let's go back to the rule. You see, here I have pi1 that implies pi3, and then I can introduce by disjunction pi1 implies pi3 or pi2, and here I have pi2 or pi1 that implies pi2, pi1 that implies pi3 or pi2, right? So you have two different formulas, pi1 that implies pi2 or pi3, and pi1 that implies pi3 or pi2, and these two formulas are not intuitionistically equivalent. They are classically equivalent, but not intuitionistically equivalent. So we need to use higher level rules. These would be the translation of this formula here, and these would be the translation of this formula here. But again, I can use Peter's higher level rules and obtain this translation and so forth. A conjecture, I don't know if it is right or wrong, I was thinking it quite recently, is that if we have this case of the flattening problem, that we have introduction rules for different operators with the same elimination rule, then I think that we have a third operator. We would have a third operator that have all the introduction rules for it, and that elimination rules that collapsed as the elimination rules for it. In the case that we are studying, this would be the operator, pi1 that implies pi2 or pi3, which is exactly the translation that the elimination rule that we had before was giving us. What is the future? The use of the reducibility predicate to prove unicity of normal form. And why one would like to do that? In the thesis of Philip Widbeck, he was a student of Dog, he proved for the implicational fragment, just for the implicational fragment conjecture concerning the identity of proof problem, right? And there he says in his thesis that it would not be difficult to extend his result to the universal quantification and to conjunction, but disjunction is something special. So given that one of the main goals of Fernando and Gilda was to study the behavior, the proof theoretical behavior of disjunction, maybe we could use the system. No, we do not have any negative result, right? It is, so far it's just difficult to extend his result to disjunction. Maybe we could use the system fat and the reducibility predicate for fat in order to extend Widbeck's result to disjunction. Another future work is to use the schematic elimination rules. The use of schematic elimination rules introduces permutative reductions too. So use for analyze those I axioms and E epsilon axioms that I showed you. And this is something which is very difficult, but it is something that one should try to do, is to extend systematic rules with restrictions, like modal operators, quantifiers, but it is, I don't have any idea of how to, to produce these extensions of this schematic rule using restrictions. And that's all. Thank you very much for your attention.
So we have time for a few questions. Very good. So, I was discussing this system with Fernando and Gilda a couple of months ago.
Yeah.
And I had the impression that this system fat should be decidable, actually.
Mm-hmm.
It's a very weak...
Very weak system. Yeah.
So do you
No.
have the same feeling?
No, I have the same feeling, but I didn't have done anything in this direction. So really my goal was to use the system, just to use the system effect in order to model any operator, right, that has schematic introduction elimination rules, and so to have a kind of general proof theory for all these operators. And coming back to your middle question, right, why can you justify that we still have the overflow? Because in fact, the general form of all these translations is conjunction and disjunction. That's the reason why. The general form, besides some formulas that do not have any variable, right, as an antecedent of an implication, the real core of the formula is disjunction, elimination, and conjunction elimination. So that's the reason why. I don't think it should be decidable, but I don't have any proof.
More question?
What happens to quantifiers, kind of traditional quantifiers? Because you're saying you want the system to prove things like disjunction property, right? And presumably existential property too. These things kind of, is the FAT system going to help with that? Kind of
to investigate extents to use the systems in order to have a kind of schematic introduction elimination rules. And because of restrictions, right, the quantifiers still do not fit with these schematic introduction and elimination rules. You must add restrictions in order to have our rules, schematic introduction and elimination rules, are completely without restrictions, right?
The rules of yours and Wang? No.
The rules of Profits, the rules of Peter Schroeder-Heister, and so forth. The one that I showed you.
More. I mean, why do we need the ether on the FAT?
These I have to show in the real reduction, right? In the way, because as I said, you do not obtain, for example, if you, let me go back to the, here. Suppose now that I introduce disjunction. Right? And suppose now that I use this disjunction as the major premise of an elimination. Right? The conclusion of this elimination can be any formula. But I cannot use, for example, this x here, that is universally quantifier, to instantiate. I must deduce, right, what I want to obtain as complex here as a derivation. Right? When I do this derivation, I introduce some garbage in a certain sense, some extra things in the derivation, and I have to eliminate all these things. And that's in the final step of the reduction of the derivation. I will have to use a neta reduction to clean, so to say, a lost garbage that I have in order to obtain a translation of the real